Alright, today I'm going to be going over number 902 numbers at most n given digit sets. So for this problem, we are given an array of digits sorted in non-decreasing order, which means that it's from, I believe the term is big endian, so like the first one is the biggest number and then it goes on and forth. And I can write numbers using each digits as many times as I want. For example, digits equal 1, 2, 3, 5. We can write numbers such as like 1, 3 or 13. 551, which is in that area, and 135, 135, 15. And basically, our goal is to return the number of positive integers that can be generated that are less than or equal to a given integer n. So I like to write down what I'm going to return first. What I will return is literally all the combinations of digits below n and need to be in the same structure as the array. This is mainly like for the digit dp portion of this, which is why I specified that it needs to be in the same structure as the array, because it's easier to represent this as like a string than a number. So they give us an example here where, for example, given like digits 1, 3, 5, and 1, 3, 5, 7, where n is equal to 100, there are 20 possible numbers that can be written using these digits, but below 100. Same thing over here for n equals 1000. There's an output of 29,523, which represents that many outputs. And here's the base case over here, where if there's just one digit, it just returns 1, and possibly 0 if n is just like less than like the digit, I would assume. So this might seem a little overwhelming at first, but I think it's possible to understand this and to also solve, as I was able to do this before. How can I draw this in Paint? I'm not entirely sure, because I think it's a little simple to understand. Hopefully this works. Okay, cool. Let me see if I can expand this. Okay, in DigitDP, or Digit Dynamic Programming, there's some keywords you want to look for. If it gives you a upper bound for n, then you know for a fact that there's probably going to be some kind of upper limit that you need to hit. So digit dp, there is some upper limit. Alright, and usually with these kind of problems, there is also some kind of weird uniqueness to them, and a lot of other factors, but for the most part, there is always in DigitDP an upper limit that you need to hit. Usually you could go with some kind of like permutation algorithm or something like that, but with these kind of problems, it's hard to really discern using that kind of solution because of this special constraint where the limit that you're trying to reach is around 10 to the 9, which is like, what is it, a billion, I'm pretty sure? Like a billion parameters, which would take like a lot of time to do like a permutation style example. So we have to use dynamic programming here in order to alleviate this this potential issue. With dynamic programming, we need to, of course, like define our state and also figure out exactly what are we trying to tabulate / memorize to save like a bunch of computational time. Alright, so let's do, I guess like 100 would be easier. So we're given digits 1, sorry for my bad writing, but this is the best I can do. So we're given 1, 3, 5, 7, and we can go where n is equal to 100. Oops, that's bad. We already went over our base case being that if n is less than all digits, then it returns 0 at best. Okay, cool. You can see me. So, what the pattern here is that we just go like between each number. Like, for example, the starting inputs are 1, 3, 5. Oh, whoops. 7, and then the next immediate number after that is 13, 15, 17, and so on. It's basically just a combination of these few letters. Usually, when you're given a vector of, well, I guess like strings in this case, but if you're given a vector of strings to represent a digit, it typically is just digit dp. With digit dp, I already went over this, but there's always, hold on, I should stop writing here. Actually, I can write, okay, there's always an upper bound greater than or equal to 10 to the 8th. There's always a vector of strings representing that digit, and there's always some sort of combinational factor with it. Where you have to like meet a certain criteria below that upper bound. This problem right here is just basically saying we need to combine this. Whoa, that does not look good. We need to combine these list of numbers specifically into this, into these like types of combinations, and then record each unique one. So what we can initially do is create like a permutation style solver where we can use like a set and a we can just use a set to track like each unique combination, then return the size. However, because our input is 10 to the 9, we'd have to do like 1 billion permutation checks, and possibly even more, because the amount of permutations could also overlap as well. Thus, we need to find a way to tabulate this problem with dynamic programming so that we can just easily solve this fairly quickly. One way to do this is specifically, given your upper bound, there will always be a sort of there will always be a limit of some kind. Usually the limit is within the upper bound itself, and that's fine. But in this one, it's just strictly with the combination of numbers we have available for us, being 1, 3, 5, 7. So in order to represent this, the easiest way would be to represent the amount of possibilities below n with some sort of memset or array. So we can use an array. Oh, why is that so thin? Okay, we can use an array to represent all these numbers. So 1, 3, 5, and then basically add a bunch of places. In digitdp, this is usually the strat where you just like make an array to represent these number of places. And in C++ specifically, store, what am I doing? Why am I typing? Store at class level, so it is rewritable. And then using that array, we can then do a list of combinations between all of them, where we basically like, what's the word for it? No, it's not roll. It's constantly like flip the digits, similar to like a combinational lock, where you like keep twisting. Let me search this up. Actually, I'm not explaining this well. I am way too sleep deprived. Where is the combinational byte clock? Yeah, similar to the combinational byte clock, we're going to just like roll these digits constantly to see how many possible combinations we have below our certain number. The best way to demonstrate this is with some sort of very large field that can contain pretty much all of our numbers. In DigitDP, for most of the time, we typically use like long hold up. We usually use long arrays to represent this because the amount of characters per digit is incredibly vast and it will take a long amount of time. So using this long array, we can just basically have this array represented as a dynamic array, and then using that we can just basically make an algorithm to constantly traverse the positions and basically ask, okay, I gotta stop typing. I gotta stop drawing my letters. Is it below the upper bound? And if it is, limit it to that upper bound. If not, roll to your heart's content. What I mean by limited to that upper bound is that let's say n is equal to 100, right? And you're currently at around, let's say that one of these numbers is like 9, for example, okay? So you had to say 9, 1, 9, 3, 9, 5. Actually, that's a bad example. Let's say n is equal to 135, and you had all these numbers. For that first digit, your limit will always be 100, or 1 at the first position right there. So which would be represented as like the third place in our array. So knowing that, we know that 3, 5, and 7 are not allowed, meaning that we can only test numbers from 1 to below, which in this case means that our only possibilities is just 1. And we can apply that same logic pretty much to every other number, as long as we first calculate this limit as well. To represent this, we can use another DigitDP method called a type bool, which just tells us if this digit is currently equal to like the position of our n upper bound, and it is an absolute limit where it's going to be like the max value, then we have this type bool active, meaning that it can only pick numbers below that certain interval. And we have the same, we can cascade that down into 3 and 5 as well. So right now we have a way to, So right now we have pretty much all the tools we need. So we have a check for is below the upper bound, and an upper bound like locator, and then we also have a type bool mechanism in order to make sure that our connection is secure. I mean, not our connection is secure, but that specifically for the digits we don't like overshoot. So now we have to figure out how to actually memorize this. Well, remember how I said that we have a long array? Because we have a long array, we can represent each possible digit, as a number. And we know for a fact that in this case it is at max 9 digits. So we can maybe be safe and just say we can create a long that is about let's say 12 just to be safe as our first row of this array. And we know that it's either going to be tight or not, so we can just say we can just dictate this as 2, and then we know that we want to calculate the amount of combinations between each possible digit. So in order to do that, we just have to have two specific cases where either it's tight in that specific area or it's not. The reason why we have 2 in our lower end is because if it were, for example, like on the lower end of numbers, and like for example, if I was at the first digit and I had 2 options. One, either the rest of the numbers are like already make this equal to 130, so our limit is 5. So we have to go with that option, or if it's below that, then that digit can be like any one of those combinations. At most, these digits will mainly contain about a value of 9 to 0 for each one, specifically showing like how many possible combinations there are. It might be more because of the fact that we're also counting for other possibilities as well. And the way we use this for memorization is that we can basically tell that if this position and tightness and comb is not already equal to -1, then we can just use that. So we can just return that specific combination at that point. The reason why we're doing this is because sometimes we'll come into possible scenarios where we run into the same combinations again. For example, like in the same 135, we might have like 5 as a last digit, and we might need to constantly like recheck that again and again and again. So thus we have that set up to be equal to that. So now we have everything we need for digit dp. We have a way to traverse below our upper bound, way to tell if it's tight, and also way to memorize. And our base case would be whenever the pose is equal to this size, being that I guess the last digit of our position itself. What else? Also, we should also be aware that we're using a recursive implementation, so we can just effectively control like our base stack whenever we need to. Okay, so with that being said, all we need to do is just implement a recursive function to specifically roll the amount of like combinations within our lock, so that we can get pretty much every number below n. So let's get started. The first thing I always do when I do these kind of dynamic programming problems is I make an array. First is the max upper bound. The second is 1 to 0 for tightness, and the third is the possibilities. In this case, it will be digit. So long memo 12 to 2. The reason why I have 2 over here is so that we can just keep track of specifically which number it's just like which case, as I said earlier, if it's going to be within that upper bound or if not, and also just in case it overflows. So we usually want to initialize this memo in the beginning, so in this case we will just use memset and the 1 size of memo. Memset is inbuilt C++ function that allows us to take in a specific container, set it to an initialization number or value, and also dictate how long we want to increase it. The size of is the amount of bytes within this memo, so it'll increase it to that amount of bytes. I mean, it'll fill up that amount of bytes with -1. And then we want to make end a string. The reason why we want it to be a string is so that we can easily like just compare between like the digits and n for the specific combinations that we need. And then finally, we will return something here, which will be our recursive function that we will implement. Of course, we need to return an int because our recursive function is going to use previous calls of our recursive function, which may involve using the memo case. Note that the memo calls, whenever we hit something, is going to be O of 1, which I'll explain later. So, DP const vector string digits, which represents the digit string we have below. Const string upper bound for the upper bound, and we don't really need to mutate these two. And we need an integer for the position that we are in within our memo. We need a boolean for type, and we need a bool for the is leading 0. Just indicating that if there's, in our memo, like if there's an increasingly long amount of zeros at the front, we just like ignore that combination at all. If not, then we can just like go back, I suppose, and then traverse it that way. This is typically the standard syntax for dynamic programming. It sounds like a lot, but once you do like a bunch of problems, you get used to it eventually. Of course, we have to do our base case, which is if our position is equal to the size of our upper bound. If it is, then we know that we've reached the end, and then we have to check if there's a leading 0. The reason why is because if there is a leading 0, then we know that it isn't valid. Because at that specific point, we don't really have a value there, and it's probably in the single digits already. So we can just say return is leading 0, 0 to 1. I'll write a comment here as well, just to indicate like what I mean by this logic. If all leading zeros should be 0, because it is not a valid position. It makes sense, because if you're at that position and it's literally just zeros, then you literally made nothing. This will be an important base case for later. Then we have our other base case for hitting the memo. We can use this to memorize our it's mainly tabulation, actually. We can use this to tabulate our results from previous runs by saying if memo pose typed is leading 0 is not equal to 1, -1, which means it's valid. We can just return that. Meaning that at that particular point we have found like we already have a value for that, and we can just return that. This isn't technically equal to the actual like digit. This is rather equal to like the amount of combinations run in the past. Okay. And then here's where we actually do our digit dp. I usually just store an answer just to make sure that we have a running sum, and a limit as well. This limit is going to be equal to how many possible digits we can run at a particular point, and if it is possible at all to do anything with that. So we can just say if it's tight, then we want to just make it equal to the upper bound. Oh, I forgot to do this. Upper bound position, so that we have a particular digit, minus 0. And then if tight is not true, then we'll set it equal to 9, meaning that we can do it to 9, so that it's valid for every single target. So for option 1, there are a few options actually. Whoops. If there's no valid digits like within our array at first, then we can just pretty much add anything. So for this particular call, we would say if is leading 0. We would say answers plus equals to digit dp, the whole call again. I forgot to put this there. Post plus 1. False for the tightness, because we already know that it's not really tight, so we can do anything at that particular position. And true, meaning that our following problem would probably have a leading 0, because the further we go along this memo, the lower in digit scales that we have. Okay. And it ties back to our first base case, because when it gets to that position, there might be some leading zeros where we didn't put anything at all. And this way, it's easier to represent this rather than having like a string of digits that we can just constantly mutate. Option 2 is that we can try placing every possible digit in that set, in that space. So we can just basically go through our every single digit, and basically just calculate that particular digit value. So we have that, and we have to check if it's now less than or equal to our digit limit. We calculate it right here, which would either be the upper bound or just 9. So if d is less than limit, we now need to calculate a new tightness to determine specifically if for future digits they have to follow the same tightness rule or not. In this typical case, usually they wouldn't have to, because it is below like a certain number, but there are some cases in which the following digits might have to follow a specific number. For example, if you were, since the number of n is 100, actually it makes more sense if it's 135. It's 135 and you're going to the next digit. You can't make this 7 because it would be greater than 3, if that makes sense. Like if we go back to our previous example. So if d is less than or equal to limit, then we have to make a new tight, which is equal to tight and d equals limit. If that's false, then that means that the future digits can run as normal. Then we have to go to the next specific possible scenario. In this case, we will just pass in our new type, and we'll keep the same logic where we keep it incrementing in position. then we finally return our answer. But first, we do have to memorize this, so in future runs, we can effectively use this in the future. So we can do this in one simple line by just saying number post type is leading 0 is equal to answer. Now that we have that, we can set up our initial test run. Of course, we pass in digits, we pass in our upper bound. What was it? We have to pass in our position. In this case, it would be 0 on the initialization. And for our limit, it would always be true because we always have like a limit, like in our first digit. And then for our is leading 0, we would also say true because there's nothing currently in there. And yeah, that's pretty much digit DP. As a result, I just need to check to make sure my syntax is correct. To summarize again, we basically first calculate how long our memorization table is. Then we pretty much figure out the digit DP, use the digit DP equation, which is essentially check if the position is. We have to make a recursive function to return like the last statements, where we have two base cases where we have to check if the position is equal to the upper bound size, and also if at our current position, if this value already exists in our table. Then we just pretty much roll through all the numbers, where typically we would always use this for loop to find the amount of like combinations below like our current limit, which is calculated by checking if we're tied or not. And occasionally we also have like an extra roll like for the is leading zeros. In other cases, it might be like if there's a leading digit or of some kind, or if you're checking like for a specific number. And then finally, we return our answer, but first set it equal. We first set our current table position equal to the answer, so that we can use it in the future. Looks like my code looks correct, so I will attempt to run it and see if I'm right. Interesting. Oh, I forgot to put D string. Okay. Alright, we got 2 of them right and 1 wrong. So in this case, we outputted 1022 when we expected 2905.22. Huh. Okay. This is the exact answer I got earlier, so I'm not entirely sure what's going on here. Maybe I made a mistake. Oh, I forgot to set it equal to limit so that we can like determine if it needs to go further. And we can go through all of them. Yep. And we should be good. Yep. We pretty much got the top result. Anyways, that's Leetcode question number 902. I'm Luis Blanco. Please connect with me in my LinkedIn, my bio. And yeah, good luck with the interview, guys.